Our fourth lesson is on Archimedes' Principle. So as we've kind of been working on the last couple of labs and stuff, um, buoyant forces are created because there's a pressure difference at different depths. So it doesn't matter what you have. You could have cork, aluminum, or lead, or really anything. But the bottom surface of the object is deeper in the fluid than the top surface. And because the bottom surface is deeper in the fluid, there's greater pressure there. And that greater pressure produces a larger force. So for something that is spherical, for example, the force on the bottom is bigger than the force on the top. And in fact, each of the forces that are near the top are smaller in size than the forces on the bottom. And so this difference in forces produces a net force which always acts upwards, and that net force we call the buoyant force. So buoyant forces are net forces which always oppose gravity. In a fluid on Earth, they always act upward. In the opposite direction of gravity. So Archimedes' principle comes from some things we sort of know and some things that are probably just legend. But the king of Syracuse, and Archimedes was his royal scientist, he had a crown fashioned of pure gold, or at least he gave his craftsmen pure gold and asked for a crown to be fashioned. And when the crown came back, the king was wondering or suspicious that perhaps he might have made off with some of the gold on his own, and the crown that he produced wasn't pure gold. Maybe it was just plated in gold or something. And so it was given to Archimedes the task of trying to determine non-destructively if it was possible to figure out if the crown was pure gold or not. So the crown itself was irregularly shaped and probably had lots of very fine delicate artwork in it. And so Archimedes was trying to figure out how he could determine whether the crown was pure gold or not without actually cutting into it or destroying it or melting it down. So that was kind of the problem that gave rise to this idea of an Archimedes principle. So the legend of Archimedes is basically that Archimedes realized you could find the buoyant force of an object by just finding the weight of the fluid that an object displaces. So this is a statue of Archimedes in Syracuse now. And basically, as the myth goes or the legend goes, he was lounging by the public pools. And when somebody would climb into the public pool, water would be displaced and would overflow the pool. The pools were replenished by naturally occurring springs. So Archimedes, upon realizing that the weight of the fluid displaced was equal to the buoyant force, the legend goes that he then ran down the street in excitement, crying, "Eureka, Eureka," basically meaning, "I have found it." And of course, he did this naked because he was so excited that he forgot to get dressed after leaving the public pool. So the myth or the legend of Archimedes is that he ran down the street naked, yelling, "I have found it," or "Eureka." Whether or not that actually happened, we don't really know. But we do know that he is the first one who, in any written way, has documented an understanding that buoyant forces are the weight of the fluid which is displaced. So what that basically means is that if you take a rock and you lower it into a beaker of water, the water level rises. This rise in water level right here, that is equal to the volume of the stone and the weight of the fluid that is displaced. The weight of this fluid is equal to the buoyant force on the stone. Calculating the buoyant force on the stone is a very nasty job involving calculus and lots of forces on lots of different surfaces and pointing in different directions. But the weight of the fluid, as we found in lab, is also equal to the buoyant force. Another way to think about it is that if you took a rock and you lowered it into a very full beaker, water would spill over. The water that spills over, if you weighed that water, the weight of that water is exactly equal to the buoyant force on the rock. So it doesn't matter how deep the rock is, it won't cause any more water to spill over once it's submerged. So the buoyant force is a constant once the rock is completely submerged, and that constant doesn't depend on how deep the rock is, but the weight of that fluid displaced is the buoyant force. So a couple of quick notes. If a stone is placed in a container of water, the water level will rise. We say the water is displaced or pushed aside by the stone. And the volume of that water that is displaced is equal to the volume of the stone. And the weight of this displaced water is equal to the buoyant force. A quick word about terminology here from our friendly mouse. If you stick your foot in a swimming pool, we say your foot is immersed. If you jump in and sink below, then you have total immersion, or what we call submerged. So immersion means partially in a fluid, and submerged means totally in a fluid. Okay, so here's a little thought experiment. If you had a brick and it weighed 3 newtons, so its weight in air is 3 newtons, there is 0 newtons in this pan right here. There's no water. You lower the brick into the water, and now the scale reads 1 newton. So it went from reading 3 newtons to 1 newton, which means there must be an extra 2 newtons of force upwards on this brick due to the water, because the total weight is 3 newtons. So what that means is that if you were to catch the water that spills over here, the weight of this spilled water, which must be the buoyant force, must be 2 newtons. So the buoyant force, which acts on this weight upwards, must be equal to the weight of the water displaced. So if 2 newtons of water is displaced, there must be 2 newtons of upwards force due to the water, which means that the spring scale only reads 1 newton. We call what the spring scale reads when an object is submerged in a fluid, we call this the apparent weight. So you may have noticed that you can hold a little kid in a pool, or things that are in a pool or submerged in a fluid aren't nearly as heavy as when they're just in air. And that's what we call the apparent weight. So the apparent weight is the difference between the true weight in air and the apparent weight when there's a buoyant force on it, which is reducing the force that's on the spring scale, or the string that's holding it up. So if an object is completely submerged, so that's like, for example, one of these 3 things, but think about that log underwater. If the buoyant force is bigger than the gravitational force, the object will float. So if you take this log and you submerge it underwater, the force going upwards is bigger than the force going downwards. The log will pop to the surface because the force on the upwards is greater than the force downwards. In the case of the rock, the buoyant force, although there is a buoyant force, it's not as big as the force of gravity, and so the downwards force wins and the object will sink. And in the case of a fish, if the buoyant force is equal to the weight of gravity, it doesn't sink, it doesn't float, it simply hovers in the water. And fish have actually what's called a swim bladder. They can take on little pockets of air and adjust their buoyancy so that they don't sink or float, that they can move at will with the water with no net force on them. So a little example of how that looks is here. What I have is a block of wood right here, and the block of wood is floating in water. And so that means, because it's floating, that the force going downwards, the force of gravity, is equal to the buoyant force, which is going upwards. So I can show that with some arrows here. The force of gravity is the blue arrow going down, and it's equal to the buoyant force, which is going up. If I were to grab this block and shove it underwater, it would displace more fluid. More water would be pushed out of the way. And if it displaces more fluid, the buoyant force on it is larger. And so now you can see the buoyant force, the pink arrow going up, is much bigger than the gravity force going down. And so were I to let go, it will pop back to the surface. So that's an example. If something is floating, then you know the buoyant force equals the weight of the fluid displaced. Now, think about a boat. What would happen if I loaded some weight on here? If I take some bricks and I put them on here, there is now more force going down, and so the block of wood sinks deeper so that the buoyant force going up is greater also. So now, because it's still floating, the buoyant force still equals the weight of the fluid displaced, but more fluid had to be displaced because there was more weight going down. If I take this brick and I put it over here in the water, it sinks. There is a buoyant force on it, but because it is a more dense object, its volume is not as large, it doesn't displace as much water, and so its buoyant force isn't as big as the wood. And so if the buoyant force isn't big enough to counteract gravity, it still sinks. But when it's down here, it doesn't weigh quite as much as it does up on up on land. So I'll put a scale underwater here. If I take this and I put it on a scale here, it reads 49 newtons. That's its true weight. If I put it over here on this scale underwater, let me move that out of the way. Now it only reads 24 newtons. We call this the apparent weight. The apparent weight is the difference between the true weight, which is basically the force of gravity, minus the buoyant force. Okay? So that's kind of how buoyancy works. Okay, so an object will float if the force on it upwards is equal to the downwards force of gravity. So if you have a solid block of iron, it will not displace very much water, and it will not have a very large buoyant force, and it will sink. No problem. If I take that exact same block of iron and I hammer it out into a shape, perhaps it looks like this, then that same iron can now displace a lot more water. You can see a lot more water is being displaced by the iron. And as long as this water doesn't come inside, as long as it's being displaced, it produces a large buoyant force which can oppose the weight of the iron. So this iron floats not because the density of iron is less than the density of water, but because the buoyant force is as big as the weight of the iron. Now, if you were to load a couple people in here, this would get pushed down a little more, and then if the water were to spill in from the sides, it wouldn't be displacing that water anymore. The buoyant force would get small, and the boat would sink quickly. So most boats have a lid or a deck which covers this so that even the waves can't splash over the side and start filling in the inside. But basically, that's how things float. The buoyant force is as big or larger than the force of gravity pulling downwards. So here's a ship. It's empty. It's floating. It is displacing water, and the weight of the water that it's displacing is equal to the buoyant force, and that's the same as the ship. If you were to load a whole bunch of soybean on there from an Indiana farmer and send it off to wherever the soybean goes, the ship would there'd be a greater force downwards on the ship, and so the ship would start to go down and down. And as it moves downwards because of the greater force of the soybeans, it displaces more water. And as long as you don't overfill it, you can get to a place where it's just riding deeper in the water and displacing more fluid, so it has a greater buoyant force. And then when you unload the ship, it would rise back up out of the water. So if you look carefully at ships next time you're near a harbor, you'll actually see markings on the hull, which basically give the weight in gross, I think they're usually kilotons, of the ship. And so as you add weight on, the ship sinks deeper and deeper and deeper into the water. Okay, so how do we calculate buoyant force? Well, to find the buoyant force, we just got to find the weight of the fluid displaced. So the buoyant force is equal to the mass of the water that is displaced times g, because force equals m times g. So this is our old equation from way back in September. Force is m times g. The mass of the fluid that is displaced can be found by taking the density of the fluid times the volume. And then we multiply that by g. So the short story is, if you want to find the buoyant force, find the weight of the fluid displaced. And the weight of the fluid displaced, the buoyant force, is equal to the density of the fluid times g times the volume of the fluid. So this is a good place to pause the video and jot that equation down in your toolbox. That is what we've been working towards this whole unit: how to calculate the buoyant force on an object which is submerged in a fluid. And make sure when you jot this down, you note the units. The buoyant force will be in newtons. The density has got to be in kilograms per meter cubed. And the volume that's displaced will be in meters cubed. And of course, you know G is in meters per second squared. Okay, let's solve 3 example problems. These are a little bit complicated, so you need to pay attention and pause the movie if you need to, as you're kind of taking notes, I guess, to kind of figure out what's going on. And then on this assignment, I'm going to ask you to show your work. So I know you've been kind of skipping along, not doing a whole lot in your books there, but this one's complicated enough that showing your work's really going to make your life easier and help you get to solutions faster. So the first question is, what is the buoyant force on a spherical golf ball? We're going to get a golf ball. We're going to submerge it in water. The ball has a mass of 32 grams and a radius of 2 centimeters. So we're going to just start by drawing a little diagram. I've got a golf ball here in some kind of bucket of water or something. And my 2 variables that I have are the radius of the golf ball, which is 2 centimeters, which I'm going to write as 0.02 meters. And the mass of the golf ball, which is 0.032 kilograms. And of course, the density of the water is 1,000 kilograms per meter cubed. In the equation using buoyant force, we're going to need our densities in kilograms per meter cubed. Okay? So to solve this problem, we're going to do a couple of steps. Remember, the buoyant force, which is what we're after, is equal to the weight of the fluid displaced. So what we're going to do is have to find the volume of the golf ball. Since it's a spherical golf ball, finding the volume, we can look up the formula for a sphere. It's 4/3 pi r cubed. And then once we find the volume, we can use our buoyancy equation to figure out the buoyant force on it. So our plan is going to look like this. Our first step is going to be to use the volume equals 4/3 pi r cubed to find the volume. If r is in meters, then the volume will be in cubic meters, so we're good there. And then we can find the buoyant force by taking rho times g times the volume. Remember, rho is the density of the fluid that we're in. G, of course, is the gravitational constant, and v is the volume that is displaced. And we're going to use that to find the buoyant force. So, step 1, find the volume, plug in our numbers, you get 3.35 times 10 to the negative fifth cubic meters. Once we know that, we can find the buoyant force. It's rho times g times v. Plug in your numbers, and you get 0.329 newtons. So that's not a huge force, but that's the buoyant force on a golf ball if it is submerged underwater. Now, a quick calculation. We know the mass of the golf ball. So if I multiply that by g, I can find the weight of the golf ball. So the weight of the golf ball is actually 0.314 newtons. So take the mass times g gets the weight. So if when the golf ball is submerged, the buoyant force is 0.33 newtons upwards and gravity is 0.31 newtons downwards, you can tell the buoyant force right here is greater than the force of gravity. The golf ball will have a net force upwards, which will cause it to rise until it just pops out of the water a little tiny bit. So the golf ball in this case is going to float because the buoyant force when it's submerged is larger than the force of gravity downwards. All right, now let's solve a second problem. So I've got a 1.2 kilogram block of aluminum, and it's going to be submerged in alcohol. So the alcohol has a density, the aluminum has a density of 2,700 kilograms per cubic meter, and alcohol has a density of 806 kilograms per cubic meter, so that's a little less than water. And we want to know, what is the apparent weight? So to find the apparent weight, we got to find the difference between the true weight in air and the buoyant force. The difference of those is the apparent weight. So let's start with a diagram. I'll use a yellow alcohol here, just so you can kind of see it. And here's a chunk of aluminum at the bottom. My variable list, I know the mass is 1.2 kilograms. And I'm going to use O for object and F for fluid in my subscripts. This is fairly conventional. So the density of the object, the aluminum, is 2,700, and the density of the fluid that it is in is 806 kilograms per meter cubed. Okay, so this is going to involve 4 steps to find the solution to this problem. The first step, we are going to try to find the volume of the object. Okay, now we know the density of the object, the aluminum. We know the mass of the aluminum, so we can find the volume of the aluminum using its mass and its volume. So we can plug in our numbers and get that. After we know the volume of the aluminum, we're going to use the fact that the volume of the aluminum, the volume of this chunk of aluminum right here, is going to equal the volume displaced, which is true if the object is completely submerged. So when you drop aluminum into a fluid, as long as it sinks, the fluid displaced is equal to the volume of the fluid. So we're going to use that. Third step, we're going to find the buoyant force, which is the density of the fluid times g times the volume displaced. We know the density of the fluid, we know g, we know the volume displaced. We can find the buoyant force. And then lastly, the apparent weight will be the force of gravity minus the buoyant force. That's basically the definition of an apparent weight. Okay? So we can do this pretty quickly. The volume displaced, this is step 2, equals the volume of the object, which we can find using step 1. Take 1.2 kilograms divided by 2,700 and you get 0.00044 cubic meters. Please save this number in your calculator. Do not use it rounded. Once you know the volume, we can find the buoyant force. It's the density of the fluid times g times the volume. We can plug in those numbers and get 3.51 newtons. So the buoyant force upwards is 3.51 newtons. And then lastly, we can find the weight, which is m times g. This is the force of gravity. So that's the mass times g, which is 11.7. So we know in air it weighs 11.7 newtons, and when it's underwater, there's a buoyant force of 3.51 newtons, and so the difference between those is what we call the apparent weight. So this block of aluminum has an apparent weight of 8.26 newtons when it's submerged in alcohol. Okay, and these will be saved for you so you can use them as a reference when you solve the problems. The last problem involves Archimedes' crown. So here we finally get back to Archimedes' Principle. He purportedly made some measurements. These aren't his exact numbers, but they're sort of give us an idea of what was happening with the calculation. Suppose you take a crown and you hang it on a string, and you find the weight in air, and it's 9.81 newtons. You then submerge it in water, and the apparent weight is 9.12 newtons. The question is, from that information, can you deduce whether the crown is made of pure gold? So, we have a crown hanging in air. It reads 9.81 newtons. We submerge it in water, and it reads a little less, 9.12. This is what we call the apparent weight, and so the difference between the two scale readings, the difference between these two scale readings is the buoyant force. Okay? So here's kind of what we're going to do. We are going to first use the fact that the force in the air is equal to m times g. We know the force on the crown in the air, it's 9.81 newtons. We know g, so we can find the mass of the crown. So the mass of the crown is F divided by g, which is exactly 1 kilogram. So it has a mass of 1 kilogram. That's our first step. Our second step is to find the buoyant force. The buoyant force is the difference between the force that is acting on it when it's in the air and the force, the apparent force. So basically, the force in air minus the buoyant force equals the apparent force. We're going to solve this to find the buoyant force. We're just going to take the difference between 9.81 and 9.12, which is 0.69 newtons. So the buoyant force upwards on the crown when it's submerged in the water is 0.69 newtons. Now, the buoyant force equals the density of the fluid times g times the volume. We know the buoyant force, it's 0.69 newtons. We know the density of the fluid that it is in, it's water. We know g, we can find the volume of the crown. So plug in our numbers and you can find the volume of the crown. 7.034 times 10 to the negative fifth cubic meters. So now we know the volume of the crown. We know the mass of the crown is 1 kilogram. We can find the density of the crown. And so we're going to use the density of the object is the crown, equals its mass divided by its volume to find its density. So take the mass of the crown, divided by the volume of the crown, and we get 14,200 kilograms per meter cubed. So that's the volume of the crown. So take its mass divided by its volume, which we found here. And, ta-da, since this density right here is not the density of gold, the crown is not made of pure gold. If it was made of pure gold, the density we would have calculated would have been the exact density of gold, and this is not. So we can deduce that the crown is not made of pure gold. Archimedes solves the problem, the craftsman dies, and the king is happy. And you get to now solve your own problems involving Archimedes' principle.